and share my screen. Let's see how it goes. Okay. So let's continue with the discussion of sparse linear regression. We started talking about the noisiest sparse regression. And so the idea is that we have this model, and theta star is sparse, and we would like to recover that theta star, but there's also noise. So we looked at this sort of regularized version of the basis pursuit idea, which is, so basically it's the same objective as the usual ordinary least squares or regression, but you add an L1 penalty here. And the lambda controls the degree of regularization. If lambda is large enough, you try to penalize the L1 norm more. And the larger the lambda gets, the sparser the theta gets. And at some point, if lambda is large enough, the only solution would be the 0. So in practice, empirically, people observe that, for example, L1 regularization usually produces sparse solutions for sufficiently large lambda. And the other advantage of the problem is that this is a convex problem and can be solved efficiently. There's also the constraint version, which is analyzed in the book. I'm not going to worry too much about this. So the goal is that I assume, let's say I assume that y is like this, and I solve this problem by plugging in y. And the question is that can I get theta hat, which is close to theta star? And without any assumptions on theta star, you shouldn't expect this to be true, because the theta star basically is not identifiable. So you could make this, you can find solutions of the least squares problem without this penalty that make this quite large. So the general idea is that we want this to hold for sparse vectors, and we hope that in the case where D is much bigger than N, but the theta star is sufficiently sparse, you still can't recover. And so, for example, if the support of theta star is S, and the cardinality of the support is little s, and the little s is much less than N, so that's the key condition. Although D is much bigger than N, S is much less than N. If we know the support, we can restrict the regression problem to just these columns of X, and it would be in ordinary least squares with, let's say, S variables and N observation. And generally, this can be solved uniquely. And traditional statistics works. So there is hope, but the issue is that we don't know this subset S. We can't restrict to these columns because we don't know it. So the idea is that can we say that this somehow picks these subsets or the support automatically and solves that regression on the desired support. Okay, questions so far? No questions. Okay, so now, in order to do that, we have to strengthen the null space, restricted null space property. And so if you go back and recall, there was this cone there, and I had this alpha equal 1 there. So now I'm adding slack here, so I can, for example, have alpha be bigger than 1. So we'll see that we'll, for example, need 3 here. And that would make the cone larger. So there are going to be more thetas that satisfy this constraint or this inequality. But it's a mild, I would say, mild extension. So I'm going to represent this with C alpha of S. But the main strengthening is this, this idea here. So the idea is that we're going to assume that for all deltas in this cone, this quadratic form is lower bounded by this other quadratic form. Okay, and if you recall what the restricted null space property was, this was saying that C of, let's say, 1 and S intersects with kernel of X is the trivial set, then you can see that this condition is equivalent. So this is equivalent to assuming that this quadratic form is strictly positive for all delta in the cone, such that for all non-zero deltas in the cone. Okay. Anyone wants to maybe comment on that? Why is that true?
I mean, if it is not true, then delta will lie in a kernel of X, which is contradicting to the
exactly.
definition of RNS.
So if not, then it means that this is 0. Equivalently, X delta is 0. So delta would be in the kernel of X. And also, so there exists, if not, it would be, means there exists delta in C1 such that this holds, which violates, there exists delta non-zero, which violates that assumption. So what we're doing here is we're bumping this condition by improving the lower bound. So we have a uniform lower bound. Not only that this is bigger than 0, but it's actually bigger than some constant times the norm of delta squared. Okay. So anyone knows why? So this condition is called restricted eigenvalue condition over set S with parameters kappa and alpha. Anyone knows why this might be called, why it's reasonable to call it restricted eigenvalue condition? What does it have to do with eigenvalues?
What I can think of here is the alternate definition of the spectral norm, where you take this delta to be all of RD with the unit vectors, or I mean all of RD, all of.
Okay, so let's.
But here you are not taking all of RD; you are taking some particular cone. So maybe that's, so you are restricting your set in some way.
Right. Okay. Good. Let me see what I did here. This is a little messed up. So let's do this. I'm gonna add a page here. That's fine. Okay, let's go back. It doesn't let me open. Sorry, I'm struggling with this a little bit. Okay, that's fine. So okay, yes, exactly. So what you said is correct. So let's go up here. So can you say that again? So
I mean, to me it seems like this is a restriction of the alternate definition of spectral norm, which is equal to the maximum eigenvalue, and the definition of that is you take the supremum over all deltas in R to the D or whatever the dimension, and this is X delta L2 norm divided by delta, and that will be equal to, yeah, so this is equal to the maximum eigenvalue. So here it corresponds to kappa, but you are also restricting your supremum set to
right. So this would be the maximum. Actually, this would be the maximum
eigenvalue of singular value. Yeah.
Yes, this would be the maximum singular value of X. Another way of doing it is to do supremum. You can see something like this: delta transpose X, delta divided by
Yeah.
delta squared should
Yes.
exclude 0. So this would be what? This would be the maximum eigenvalue of x transpose x.
Yes.
Okay. How about the minimum eigenvalue?
You take them as infimum.
Yes. So take
Rather than
infimum delta in R not.
Oh, I see. I see. So that will give you kappa, not quite, but then you take.
Yes.
I
So
see.
if I assume that
Okay.
this lambda min is bigger than or equal to kappa,
Yeah.
right?
Mm-hmm.
Then what I conclude is what?
What do you mean?
I can say that this is the infimum is bigger. I can conclude that this is bigger than this for all
yes, yes, yes.
delta in RD actually, because 0 is also included. And for the 0, this is going to be
Yes.
true trivial.
Yes.
Okay. And this side you can see is x delta squared, right?
Yes.
And so this is actually, if you want to be, this should be kappa n, for example. I mean, this is different kappa than this, but you can see this is the condition. So this bigger than, let's call this kappa times n, rescale kappa. So this would be 1 over n here, right? So this condition is saying that the bound on the, so what I'm saying is that lambda min x transpose x bigger than or equal to kappa n is equivalent to 1 over n x delta squared bigger than kappa. Right, so these conditions are equivalent. So this condition for all delta in RD is equivalent to assuming that the lambda min of x transpose x is lower bounded. Okay, so what we're doing here is that we're assuming this condition, but restricted to some deltas. So that's why it's called restricted eigenvalue. So it's some sort of a restricted lambda min. Okay, does that make sense to people? Should probably take this out, maybe leave, and so questions? Let's do this. Do it here. Oof. This guy. Maybe this one as well. Leave. Okay. Everyone happy with this? So that condition is called, yeah, go ahead.
Can you just explain the line greater than or equal to Kn? That's the part.
That's the assumption. So I'm assuming this. So assume. Okay, assume this. Right?
Yeah.
Then what I'm saying is that then it follows that this has to be true. This other line has to be true. Does that make sense? So the thing is, the infimum of this is, so let me do it one more step here. Oh, sorry. Yeah. So what this is saying is that delta transpose x delta divided by this squared is bigger than or equal to kappa n for all delta in RD. Because the infimum is bigger, all of them have to be bigger, right?
Yes.
And so just multiply both sides by this, and so you get this inequality for all delta, right?
Where did the n go?
I put the n here, so I put it on the other side.
I'm sorry. I thought the underbrace was like a fraction. I'm sorry.
No, yeah, so that's bad. Okay, so yes, so this is equal to that, and then this is equal to 1 over n x delta. Yeah, I should have written it a little bit clean.
Thank you. I'm sorry.
No problem. For all. And then all of these are reversible. So this is basically equivalent to the previous one. These are equivalent. Okay. Okay, other questions? Okay, so this is restricted null, or sorry, restricted eigenvalue property, which is the name comes because it's some sort of a lower bound on the minimum eigenvalue, but not the real minimum eigenvalue. It's some sort of restricted minimum eigenvalue of x transpose x. And it's an extensional restricted null space property. Okay, so why this is useful? This is more or less the condition that you need for Lessa to succeed in high dimensions. So here is a result. So suppose you have y equal x transpose, sorry, x delta, sorry, x theta star plus w. That's our setup. X is in n times d. Delta theta is in rd. And I'm going to assume that the support of s, so support of theta star is s, and the cardinality of s is little s. Okay, and then I'm going to assume that I satisfy this restricted eigenvalue condition with constants kappa and 3 over s. Okay, so what I'm saying here is that we say that RE basically kappa alpha holds. Okay, when I'm taking alpha, I'm taking alpha to be 3 here. And kappa, I let it be general. Okay, so what we're saying that over that cone with a factor 3, we would have this restricted eigenvalue property. Okay, so this is the main condition. So it's a property of x. So x has to satisfy this. This is a notation that I've defined here to simplify our life. So z is 1 over n x transpose times w. Okay, so it's a vector in R n. Okay, and y is also in Rn. So this is this result is saying that if you take lambda, the regularization parameter, to be bigger than 2 times the infinity norm of the z, then you have it bound of the desired form theta hat minus theta star is going to be bounded by this quantity. Okay, so this kappa.
So z lies in R to the d, right?
Yes, sir. R to the d. Yes, thank you. Yeah, so the other side is, yeah, so you can see the restricted null, the eigenvalue constant appears in the denominator. So when, like, if n this is 0, the bound is not good. So you need some positive kappa. But assuming that this is a constant, this whole thing would be a constant. And then the bound scales like lambda times root s. Okay, and then you have a similar result for the constraint Lessa, which I'm not going to over. Okay, so what we care about is this bound now. Okay, so I would like to basically focus on this. Okay, is the result roughly clear? So there are 2 assumptions, restricted null space property and, sorry, restricted eigenvalue condition and the regularizer being sufficiently large. So this in itself might not be very informative. The result is deterministic. There is no assumption about W being noise. So as long as this holds for X, and so W appears in the definition of Z, you can see lambdas and Z have this relation, then this result holds. Later, just in the next slide, I'm gonna show you what happens when you have noise, and maybe then becomes clear what this bound means. So suppose I have, for simplicity, Gaussian noise, okay, with a diagonal covariance matrix. So the entries are IID Gaussians, right? So this should be more or less obvious to people. The entries here are IID normal, mean, 0, and variance sigma squared. I'm going to assume this normalization, which came up in our discussion of restricted null space property, I'm going to assume that the columns of X, so Xj is the jth column of X, when I divide them by root n, the maximum is at most C. Okay, this is not restrictive because I observe X, I can renormalize all columns so that the maximum is a given number. Okay, so this is Xj, this is n by d. So we're normalizing, let's say C could be 1, for example. We can normalize such that the maximum norm of the columns of most C times root n. Again, this is without loss of generality because you can always rescale. Let's say the entire matrix by a constant. It doesn't change the problem. And then you can also rescale y. So I can rescale x and y such that that happens, and that shouldn't affect the solution. Okay. So without loss of, yes.
In your previous slide, slide number 18, so the error bound is kind of, it is indirectly depending on the noise W. So I thought that it would directly depend on the L infinity or some measure of the noise, but it is depending on, like, you first do transformation with X, so you say X transpose of W, and then it depends on that, right? It
Yes.
is not depending directly on the noise.
Yes, that's what this result is saying, which is not necessarily bad.
Yes, could be bad or good, but it depends on what your X is.
Yes, that's right. But that makes sense if you think about it. It's not.
How?
So if, let's say, X transpose W is, so X transpose is D by N, right?
Yes.
So if I, for example, if D was less than N, so if D was less than or equal to N, then X transpose X was invertible. So I could multiply both sides here, so I get X transpose Y is equal to X transpose X times theta star plus X transpose W. Sorry, right? So if X transpose W is nearly 0, let's say W is in the kernel of X transpose, then I can recover theta star exactly. So I can multiply both sides by this implies that theta star is X transpose X inverse. X transpose Y. This is actually the OLS. But theta star would be recovered exactly. Okay, so the noise could be large, but X transpose W could be 0, and I can recover perfectly. Does that make sense?
Yes. Yes.
Yeah, so the noise itself is not important. It's somehow the components of it in the direction specified by multiplying by X transpose.
But there could be some cases where the noise is amplified when you do X transpose W, no?
The issue is that the component of the noise which is not in the span of the columns of X does not matter. So only the part. So what matters is the component of noise in it's the image of X, or the column space of X. And this is sort of showing that, right? So you don't care about the components of them. So this is Z basically is 1 over N. You're taking the inner product of the, let's say, columns of X.
Yes.
So
That's what I'm not able to understand. Why is this true in a general case when whatever the N and D is? Why is this true in the general case that it only depends on the, the columns like X transpose W? Why the error only depends on that, not W? That's what I'm not.
This was not a necessary result though. This is a sufficient result. So this is saying this bound holds. But what I'm trying to do is trying to convince you that this is a reasonable thing. So this is 1 over n, the inner product of x1 with W.
Mm-hmm.
So this is measuring how much W is in the direction of the columns of X.
Yes.
Okay?
Yes.
And this is what you care about, because the components of W that are orthogonal to all the columns, they don't matter. So if you perturb the observation in the direction orthogonal to the column space of X, then that noise shouldn't affect the estimation process. You can basically project everything onto the image.
Got it. Okay.
Good.
Okay. Thank you.
No problem.
I have a question.
Yes.
So
Go ahead.
I'm noticing that like the regularization term is a 1 norm, and this condition has to do with an infinity norm, the dual
Yes.
of the 1 norm. Can you articulate this, or maybe it happens later in the slides? Just like, is there some kind of like primal dual optimization happening here?
So primal dual optimization also comes in, yes, but there is exactly what you pointed out. So infinity is the dual norm of L1, and that's exactly why it appears here. So we're going to go through the argument, and you'll see where it comes. This is actually an application of the Holder's inequality. And if you started from a different norm, to a certain extent, you could extend the argument. And in fact, one chapter of your book, which is, I believe, chapter 9, forgot exactly, but it's talking about general decomposable regularizers. So this argument that we're going to do actually goes true for a general decomposable regularizer, which is often a norm. So if you have a norm which is decomposable in a certain sense, that we'll talk about a little bit in the proof, then yes, this condition can be replaced with the dual norm with that. But I'm not going to do the general case. Maybe one of you can present the general case. But if we go through the proof, and you'll see how this comes about.
Okay.
But you're exactly right. So this is the dual. So the dual norm of L1. And the primal dual sort of ideas also matter. So this is a convex problem, has a dual. You're not going to use it in this proof, but there's a later proposition in this chapter which I'm going to skip for now. If we have time, I'll come back and maybe talk about it, or someone else can talk about it. It's about support recovery. And that sort of proof uses the so-called primal dual witness construction, which is trying to find a primal solution and a dual solution at the same time, such that the KKT conditions are satisfied. And so there's a lot of connections with primal dual sort of representational convex optimization problems, and also the dual norm of a norm. So we'll see some of it in the proof. But thank you. Did that answer your question, more or less?
Yeah.
Okay. Yeah, just be on the lookout in the proof, see where it comes in. Okay, other questions? These are all good questions. Okay, let me show you why this is useful.
I have a question.
Yes, go ahead.
The norm of xj here, which norm is this?
This is the L2 norm. Yes, thank you. When I don't write it, it's generally L2. Okay. Sounds good? Did that answer your question?
Yeah.
Yeah, okay. Yeah, this normalization is actually going to be used in the next result. So this is, I believe, your homework sheet, the first problem in your homework sheet, I believe. So it's easy, fairly easy for you guys to show that with that normalization, this thing Z, so remember Z is 1 over n X transpose W, and W is a Gaussian. You can show that the infinity norm of Z is going to be bounded by this quantity with high probability. high probability being this 1 minus this guy. So you can see the n there sort of appears. So this is a high probability result. As n goes to infinity, this goes to 0. So the bound holds with probability 1 minus something as small. And again, you can see this is L infinity, and then the log appears, log d appears, which is not surprising. And then I'm dividing by 1 over n, and there's this normalization, so there's root n involved. So this is also not surprising, but once you figure it out in the homework problem, it becomes clear. The log d appears because of the L infinity norm. And this is the significant part of the result, because then I can take lambda to be this quantity. Okay, I need an upper bound on z, like the L infinity norm. So lambda over 2 needs to be, so we need lambda over 2 to be bigger than z infinity, just bigger. And what I'm doing here is I'm just taking lambda to be this. You can also take it to be larger, but let's say take it to be exactly this, because you can see there is a trade-off. So if lambda is large, the bound is going to be, the larger it is, the worse the bound gets. So you want to take lambda to be as small as possible. So we're going to take this to be exactly 2 times z infinity. So if I take that, I get the best result. So I'll take it to be the bound that I have on z infinity. And so the result translates to this. So 3 over, so this is twice this. Okay, so there's a 2 here. And so I get twice, this is basically 3 over kappa root s times lambda, where lambda is this guy. Okay. That's the lambda, goes there. So you get this bound. And so let's treat this part as constant. And if I take delta, and this holds with high probability, with this probability. So if I take delta to be of the same order as this, so I'll take delta to be root 2 log over n. So take delta to be equal to root 2 log over n, log d over n, sorry, log d over n. Then what I would get is, this is bounded up to a constant what I would get is basically, let's say, equal to 12 c sigma over kappa root s root 2 log d over n. Okay, and this is going to be, if you ignore the constants, the key parts are sigma, this, log d, and n. Okay, so what you get is this result. Up to constants, it would be sigma root s log d over n. And delta, when I plug it in here, I get, this is going to be d. Log d, sorry, log d. So I get, this is going to be 1 minus 2d negative 1. Okay, which is just this guy. So we managed to prove this. So combine this idea, which you show in your homework problem, this result, with, or rather this result, with this result, and you get a nice upper bound. And you can see this upper bound grows logarithmically in d. So as long as log d is much smaller than n, d could be much bigger than n, but log d could be smaller than n. This could go to 0 as n goes to infinity. So d could be as big as exponential in n, and you still get consistency, which is interesting.
So S here is the size of the support of theta star, right?
Yes.
And so what range of S does this result hold for?
So this holds for any S, D, and N.
Any
so
S between?
So this bound holds for, this is like a part of this, the book is about like the high dimensional statistics, non-asymptotic. So this is a non-asymptotic result. Non-asymptotic.
So this holds for any
Holds
s between up to n.
for any s, no, for any s, d, and n, whatever you want. So s could be 1, could be d. But the bound might not be good. So if s is d, this would be d log d over n. If d is bigger than n, this is not a good bound.
So this holds for all values of st.
All values of s, d, and n.
I see.
Yes, this is one of the advantages of working with concentration inequalities. They can also give, like, you have explicit constants here as well. So if you want, there are these constants there.
Yes.
And you have a result which holds for any values.
I see.
Yes, okay, good question. Other questions? Clean this up a little bit. Log D.
I have kind of a question. If
Yeah.
D is really, really big, much bigger than n, then lambda is likely to be pretty big. Like, it's unlikely that the noise would be perpendicular to most of the columns.
So can you say that again? What was the assumption?
Like if you have a really, really wide design matrix, it's very unlikely for the infinity norm of z to be small. Like, it's very likely for the noise to correlate with at least one of the columns, right?
Okay. So if D is big, the idea is that D could be very big, so you'd have, because it's a random Gaussian, right? So you could have, because it's an infinity norm, so you'd see if you try to prove it, you would need, you do a union bound, okay? And these things are gonna be, so you're gonna look at these things. And these things are gonna be small with exponential probability. And you do a union bound, there are D of them, you pay a price of log D, okay? So you could still guarantee that this is small. So basically you would guarantee that this holds. This is saying that this is small if log D is smaller than n. It could be very wide, but the log of D could be, let's say, 1 over 100 times n. Okay, then this would be a good result.
Okay.
Right?
Okay.
It's not that obvious. Yeah, so they're random. The majority would be 0. The fact that one of them by chance is really large is controlled if the number is not too big. Too big means it could be in the exponential of, like, D could be like in this problem. These are good questions. So D could be like e to the negative c times n for c is small enough. And this side would be small enough. Okay.
So when you
Positive
say
c,
it's just
positive,
union bound.
yes.
It just follows from the union bound. That's it.
Yes, that's your homework problem.
Okay, cool.
You would, yes, follows from union bound and concentration of Gaussians or sub-Gaussians. So each one of these would be sub-Gaussian in this case, actually, or sub-Gaussian in general. So this result also holds for sub-Gaussian design. I'm doing it for Gaussians for simplicity. Yeah, so D could be e to the c times n, where c is much smaller than n, which is surprising. So the dimension could be, I mean, if c is constant, small, then the other side is not going to go to 0. But let's say if c slowly goes to 0, still this could be pretty big. So you could, for example, have, could take c to be 1 over log n. Okay, then you'd have e to the n over log n, which is pretty big, but then log d over n goes to 0. And you get a non-trivial result. Okay, sounds good.
So this line is kind of like, I know it's like a really basic step in this proof, but it's kind of like a lower bound, or it's kind of related to the random matrix projection that we talked about earlier. Like if you project onto a random matrix, you're likely to be able to represent your data well. And this says that if you take the inner product of like random noise with the columns of a matrix, it's actually not likely to correlate with them with any one column very much. I don't know, is there a connection there to think about or not really?
So these things are all related. Yeah, so random high dimensional vectors have certain interesting properties. That one was the one that we mentioned in the Johnson-Lynch draws. So there you care about the L2 norm of the projections. Here, yes, you have just a single vector, but you're taking the inner product with deterministic vectors. And the idea is that the fact that by chance one of them gets really big, this is the chance of it is small if the number is not super exponential, like exponential, but not that much bigger than exponential. Okay, it's related, all related to these concentration inequalities. But I don't have like a specific, there are various other ways of characterizing these things, but these are aspects of the same idea that when you do let's say when you work with a high dimensional random vector, let's say projections of it concentrate. So here you have like, you're projecting basically more or less projecting the random vector onto different directions, and the idea is that almost all of them, or all of them with high probability, are going to be small if there are not many directions. Does that make sense? So geometrically it's hard to visualize, but intuitively this one at least is intuitive. So a random vector in RD is not going to have any like significant component in the direction of a single direction. So if you pick a deterministic direction, so U transpose W is going to be small if U is constant. And if you have like many U's, but it's still finite, and the number is not too big being in the order of exponential let me see. So the number is actually, sorry, yes. So this is yes. So W is in Rn. So this is in Rn. The number of these vectors would be D, and as long as that D, the number is small enough, could be still exponential in it, but as long as it's small enough, then these things are going to be still small. I don't know how useful that explanation was. Did I answer your question more or less?
Yeah.
Yeah, I don't see a direct the direct connection between the two, but these are all, there you had like a random matrix, and you projected a bunch of vectors on that. Here we have a single random vector, and then is it projected in different directions. But both relied on the concentration of something. There it was the like some sort of quadratic form, or chi-square type random variable. Here is just the absolute value of a Gaussian. But then there's also union bound involved. So they are related. So the ideas are related. They can take a closer look. Maybe you could come up with something more interesting connection. Yeah. Okay. Other questions? These are all good observations. Okay. So what we have here is this result, and so this is the typical high-dimensional scaling sparse problem, S log D over N, and if we knew the support in advance, what we would get would be something like that. So I can't, for example, or you can show with high probability you would get, if you solve the regression on the support, the actual support, you can get a bound which is sigma root S over n. And you can see the price of not knowing the support is this extra log D, which really is not that big of a price. And this is the price of roughly the price of searching over these D choose S candidate supports. And I'm not going to show it, but it's like in the final chapter of the book. This is unavoidable. So this log D you can't get rid of without assuming the support in advance. So you have to pay a price for not knowing the support. But this is basically no matter what method you use, but this is as good as it gets. So this so achieves the sort of optimal scaling in S, D, and N. Okay, questions? Okay, so if not, let's try to prove this result. So this part you already do in your homework, so what we need to prove is this theorem. So in order to do so, let's introduce this notation. This is the loss function. So the optimization is going to be given this notation. The optimization will be argmin over theta of L theta plus lambda theta 1. Okay, so this is the data dependent part of the loss. And I'm going to define this extra vector. So delta would be theta minus theta star. And instead of working with theta, I'm going to work with this deviation. And a little bit of algebra. So if I plug this y is plug what it is. So x theta star plus w, then you'd see that I get this equation, okay, from the definition. And then I also get this one because these two are the same. So theta minus theta star replaces with delta. I get that. And then you expand. You get this term plus this term plus a term which is going to be 1 over 2n norm of w squared. But from an optimization perspective, because I'm trying to optimize over theta or alternatively delta, this is going to be a constant. So we're not going to worry about that. Write it as a constant. The next step is just replacing this with that. So why is that valid? Anyone?
X transpose is the adjoint of X?
Yes, so that's like the functional analyst way of saying it. So yeah, so this is X transpose is the adjoint, and this is the definition of the adjoint. That's a good way of looking at it. If you don't know what an adjoint is, you can either look it up or just remember that X delta W is just X delta transpose times W, the delta transpose X transpose W, which is just delta X transpose W. So for vectors, it's just easy to verify. But in general, I can just move this operator to the other side and flip it to the adjoint. That's the definition of the adjoint, which turns out to be the X transpose for a matrix. And now I have this combined with this. If I move on over n there, that would give me Z. Okay, so now I've simplified this to that. That was the definition of Z. Right, remember, Z was 1 over n X transpose W. Okay. So far, so good. Next, we note that if I apply this to, if I want to compute L theta star, I just have to plug delta equals 0 here. So these terms would go away. I just get this constant. So when I subtract L theta 0 from L theta, I basically conveniently remove this constant. So I get this expression. So I have this equality basically. Okay, so this is some sort of an expansion of, it's like a Taylor expansion. It's in fact a Taylor expansion. This is a quadratic form, and this is actually the second order Taylor expansion of it. but we have derived it without taking derivatives. If you want, you can take derivative, and you can see that this is the first order term. This is the second order term. Okay. Okay, questions? So we haven't done much yet. We just rewrote a bunch of things. Now this is the, well, actually this is the constrained version. I guess I'm going to prove the constraint. So let's prove the constrained version. So the constrained version is similar, you can see. The idea is that I'm going to solve argmin y minus x theta, because this is easier to prove, I guess. So theta less than or equal to r, which is, I'm going to assume that you know the actual L1 norm of theta star. I don't know theta star, but let's say I know that the norm of it for simplicity. So I can solve this. This is going to be L1. So L1 norm of theta is less than or equal to L1 norm of the actual theta star. Then what I would get is, instead of lambda, I get this result. So there's no lambda, I just get the z infinity there. Okay, so let's prove this result first. It's actually, I could have skipped this, but let's do it because it's simpler to prove this. So I'm proving. So theta hat here is argmin theta L1 less than or equal to theta star L1 1 over, let's say, 2n if you want, y minus x theta L2 squared. So this would be basically argmin L theta 1 less than or equal to theta star 1. So it's a constraint optimization problem with this L1 as the object. Okay, so the first step is the so-called basic inequality, which is, if you've seen the 200B, when we tried to prove consistency of M estimators, we did the same trick. So we're going to say that theta star is feasible for this problem, which means that it satisfies the constraint. I've set up the constraint such that that exactly is what I need. I did satisfy, sorry, the constraints are set up such that this holds, so theta star is feasible, and theta hat is optimal. So I should get that L of theta hat is less than or equal to L theta star. So this is a basic inequality that should hold for any optimal solution. Okay, does that sound good?
Yes.
Yes, so if I define delta hat to be theta hat minus theta star, what I would get here is I would get theta hat here, delta hat here, right? See in the previous slide. And what I've shown is that this side is negative. Okay. Then it means that this inequality should hold. So if I rearrange this side, I get this expression. Okay. So this is our basic inequality, basically. So it controls the deviations of delta in if you want this type of norm in terms of the side depends on the noise. So we need to now manipulate this to get the result. Okay, so that's the starting point. The next step is to do the Holder inequality. That's where the dual norm comes in. Okay, so I'll do the Holder inequality. So everyone knows, how many people know what the Holder inequality is? Maybe you can do it in the participant window. Yes, no. Like vote there. Click on participant. Yes. Yes. Okay. Yes. 5 people. No. Okay. So what is the Holder inequality? Maybe someone wants to remind us or recall what it is. So if I have x, y inner product less than or equal to.
Yeah. So if P and Q are any two numbers so that 1 by P plus 1 by Q is 1, then yeah, then this holds.
Right. This is like an extension of the Cauchy-Schwarz, which would be the case where P is equal to Q is equal to 2. And this holds if P is anything between 1 and infinity included. So when P is infinity, Q would be 1. So I would have xy is less than or equal to. And this version is really simple to show, actually. There's no difficulty in proving this. Try to do it. It will be just triangle inequality and properties. But we'll use this. I'm going to bound this side by the absolute value and then by this. Okay.
This is easy. Yeah.
Okay. Now I get this L1 norm of this conveniently here. And then I can use the property that I assumed about the cone. So what I'm going to try to show is that this inequality that we have here, so we're going to show that this inequality forces delta hat to be in that cone that we wanted. So that cone that controls the off support L1 by the in support L1. Actually, in this case, I don't need 3. I need just 1. For this, 1 works. So here's what I have written. Because this is true because theta hat is feasible, then I have this belongs to that. So can anyone justify this step? Why, if theta hat is L1 is less than theta star, then delta hat is in that cone? That's the key part. Actually, this is not going to imply, in this case, I don't use this. So yes, so this is not, this is enough in this case. We'll see in the other case, the inequality is going to force it. But in this case, just the feasibility condition will force it. So let's go back. Remember the calculation that I did. This is basically the same argument here, right? So what we are doing here is saying that, remember delta is in T1 of theta star. So this is exactly the same calculation that we did. So delta in T1 of theta star is equivalent to saying that theta star plus, let's call it delta hat, plus delta hat L1 is less than or equal to theta star 1, okay? Right, so that inequality that I had there says that, remember this?
Yes.
So this is saying, basically, this is saying, this would be equivalent to delta hat belonging to that tangent cone. So delta hat would be a descent direction on L1. Because theta hat is theta star plus delta 1. Sorry, plus L1 over delta. So that's, and then I'm going to use the idea. So I'm going to expand. Then we do it there. It's the same argument. Have it there, it would be easier. So we would have theta star plus delta hat is less than theta star. Okay, I decompose it into 2 pieces. Theta star S plus delta hat S, right? Plus theta star S complement plus delta hat S complement less than or equal to theta star 1. This is 0, right? By assumption.
Yes.
And I'm going to move this to the other side. Move to the other side. So what I would get is delta hat S complement 1 is less than theta star 1 minus theta star S plus delta hat S 1. Okay, let's see if I can move this to a new page. Or I'm going to be. No, it didn't work. So it goes up. So let's do it here. Fine. Okay, so let's call this star. Okay, so what do we get now? What is the next step? Clean this a little bit. Minus theta S plus delta hat S 1. What is the final step?
Now you can take soup over all theta star, which is subset whose support is in S. Then you apply.
Right, but I don't need the soup. Just triangle inequality would do, right? Can I do triangle inequality? Just theta star is fixed, let's say.
Yes, you can do triangle inequality, and yes. So theta star L1 norm is equal to theta star of S L1 norm.
Right.
Yeah.
So you're right. So let's do that step. So this is theta star S complement. Sorry, S L1.
S,
right?
yes. And now, and that second thing is less than or equal to theta star S minus delta, and minus will be plus.
I hope you agree with this. Okay, so this is like saying
yes.
Right. So saying X L1 minus X plus Y L1 is less than or equal to Y L1, which is a version of triangle inequality. Does that make sense to people? Is this triangle? This holds. Right? I can say this is like X plus Y minus X. Right? A, B, B, A. Does that work, more people? The norm of A minus norm of B is less than or equal to norm A minus B. This is a version of triangle inequality. So if I apply it with delta S minus, I can drop the absolute value, I get another bound. This is less than or equal to the difference, which is going to be theta. Okay, so that's an application of triangle inequality. So I showed that this is bounded by this. Hence, we have shown that delta is in fact in C1 of S. Okay. So the only thing that we needed is this. This is actually, again, in this case, nothing but saying that delta hat is a descent direction of theta star, and the idea is that if that's then it has this cone condition. Okay, now I can do a little bit more. So I can now write down the L1 norm of delta hat. This is going to be L1 norm of delta hat S plus the L1 norm of delta hat S complement. This is another sort of application of decomposability. This is, let's say, one application here. This is basically decomposability. We have L1 norm. I can decompose it onto the support and off support. So decompose it into two pieces. The L1 norm is the sum of the two. That's critical. And I'm doing it the same here. So another form of the decompose, like another application of decomposability. Decomposability. of L1. So now this is the case, then I can bound this part by this part, right? Because I've shown that this is bounded by that, so I get twice this. So this is going to be an upper bound, right? Just bound this by delta S L1 because we just showed that it's in the cone. And so I get twice that. Right, so the entire L1 norm of delta is bounded by twice the L1 norm of the support. L1 norm of the unsupport part. And then I have this inequality. So why this inequality is true. Now I can translate.
Yeah, you can use the Cauchy-Schwarz again.
Yes, so we can use the Cauchy-Schwarz. This is saying the L1 norm is less than root S. This is an S-dimensional vector.
Yes.
The L2 norm of this. And this is bounded by the L2 norm of the whole thing. Okay?
Yeah.
People are fine with this? Try to show this. This is true for an S-dimensional vector. In general, if X is in RD, then L1 norm of X is bounded by root D times the L2 norm. Okay, on the other side, it's just bounded by L2. So these inequalities hold. So the issue is that you pay a price of root D here, whereas by doing this, I bounded this by the L1 norm of this piece, and then I bounded that part with this, and then I get that. So in the end, if you look at the whole thing, what I've managed to show is, so if you look at this guy, let's look at this piece. This is, so we managed, showed delta hat 1 is bounded by 2 root S delta hat 2. So much better than delta hat 1 less than or equal to root D times delta hat 2, which you would get for a general D-dimensional vector. Okay. So we pay the price of root S in doing that translation between the two norms. Okay. So we're almost done. So now I have a bound here. You can see there's this bound. In terms of the L2 norm, I'm just going to replace it here. So what I would get is this thing. Okay. And then I'm going to lower bound this side. So let's do it here. So final step of the proof. So what I've shown is that this guy, X delta hat 2 is less than Z infinity L1, right? What I'm going to do is I'm going to lower bound this by 1 over 2n kappa delta hat 2. Why is that valid?
Because of the Kappa-Epps alpha condition, RE condition.
Right, the RE condition. So for any delta in that cone, I can do it. So we're assuming. We're assuming RE of, let's say, for this actually you need it with kappa, and we're assuming it this, but this is better than RE of kappa and 1, which we need. Okay, so delta hat, since delta hat is in C1 of S, and RE of kappa 1 holds. Okay, that's the assumption that we have. So better. Same words in any. This is stricter. So if we have this, then we'd have this. So that's that part.
But you showed only for alpha equal to 1, which is little weaker than alpha equal to 3, right?
Right.
Or,
What I'm saying is that we're assuming it's for alpha equal 3 in this problem because I wanted to hold for both parts. So for part B, I just need the RE of 1.
oh,
Okay.
yes. But
That's what
where
I'm
do
saying.
you need this alpha equal to 3? Where?
Sorry? And for the
Where do
lasso, for the regularized version.
Oh, okay. Yes.
Not for this problem.
Okay.
Yeah, so if you want to be better, you could just separately state the results.
Okay.
Okay, that's this. And the other side, I'm going to bound by z infinity.
2 root
And
s.
then 2 root s, this, right? And then furthermore, I'm going to bound this by lambda root s.
L1 norms, L2
S.
norm.
Oh, sorry, right. Correct. This should be 2. And then because lambda is bigger than 2 z infinity, I'm going to do that. Okay. So we've shown is, so we conclude that 1 over 2n kappa delta hat 2 is less than lambda root s delta hat 2. Okay, cancel one of these and then you get, what do we get? Oh, sorry, there's an extra 1 over n here. Yeah, there's no n here. This should go away. Right, so in the definition, the way I defined it, so one side doesn't have 1 over n. Okay, so this is the correct one. And so what I would get is delta hat 2 is bounded by 2 lambda root s over kappa. That's the result I want. Okay. Does that make sense? Right, so this is the result. So delta hat is the difference here. So I actually prove it with the factor of 2. Either I made a mistake or 4 is not the best. Let's see if we made a mistake here. Oh, so there's no lambda, sorry. I was confused with it. So in this case, there's no lambda, right? So let's forget about that because you're not working with that. So there's no lambda, it's just have z infinity here. And so I get, sorry, 2 times. So 2 times z infinity root s delta hat 2. And so I get 4 root s z infinity over kappa. Okay. Yeah, we're out of time, sorry. Any questions? We're gonna come back, I'm gonna come back and do the lasso one next time. And it's gonna be similar, a little bit more tricky. But it's worth going through this. I'm gonna post this. Go over this for yourself and see if you have any questions. Questions, comments?
So this bound is better than the trivial one if infinity norm of z divided by kappa is less than 1. So I mean the trivial bound is L2 norm of delta hat is propounded by L1 norm of delta hat, and L1 norm is 2 times root hat. No, it is no. Oh no, sorry.
No, yeah. So this is not a trivial bound. So you have to.
Yeah.
Yes. Yeah. Okay. Other questions? Okay. If not, thank you, and
thank you.
see you. No problem. See you hopefully next week. Okay.
Yeah. Okay.
See you guys.
Bye.
Bye. Goodbye.
Bye.
Recommended topic. So, can you maybe ask your question yourself? What do you mean by, you mean regarding the project?
Yeah, I mean the project.
So I would suggest if you want to pick a chapter, just read through the chapter a little bit, and then there are like notes, bibliographic notes at the end of the chapter. So you can take a look and see what they're going to follow. Those papers, those are probably like a little bit older now.
Oh,
And
so
follow
we
recent.
just follow the notes and read some related papers, right?
Yes,
Oh,
read some related recent papers, let's say. You can also work on like the basis could be that chapter, because we're not gonna, if you're not gonna cover it, I'm not gonna cover most of the chapters in the later part of the book. So you can take the base there, but it would be nice to see the recent literature from that bibliographic note. Just follow who cites those papers, and then see if there's like a popular recent paper on the subject, and it would be nice to sort of present those or survey it. Okay.
Okay. Thank you.
Sounds good. No problem. Okay. Good. Goodbye.